Okay, let's get going. So today we're going to talk about a bunch of things. The first thing, I don't know if you guys heard about this heartbleed bug that was like announced a couple days ago. It actually ties exactly into what we were talking about as far as web security and hashing. And well, this doesn't have necessarily to do anything with hashing, but it is about web security and about the failure of a fairly large part of web security. So we'll talk a little bit about that. Then I'm going to talk about the final assignment and give you guys a chance to ask as many questions right now as you want, and then we'll go. Then you'll be able to start work on it. There's actually two parts to it, which I'll talk about. One is the design document, which is just a text file saying what you're going to do, and then the actual code itself, which is going to be a little bit later. Then one of the things you might want to use, one of the abstract data types you actually might want to use for your project, which we never talked about in here, is a thing called a set. And I will show you how to use that. And it's pretty straightforward. And you may or may not want to use it. It's completely up to you. But I just figured I'd show it to you just in case, so you knew it existed. And then we will talk about these things called graphs. And my laser pointer is already dead. I'll go to the, where'd it go? Oh no, there's the, we used to have the, there used to be a nice long stick. Oh well, I'll just have to point a lot. So anyway, we'll talk about graphs, which may or may not be what you think about when I say graph. So we'll get into that. Questions before we get going? Nope. All right. So this heartbleed bug. So this came out a couple days ago, and I said, whoa, that's exactly what we talked about kind of in class in terms of web security. And I did not add a backdoor into anything just to prove that it's possible. No, somebody asked me that, and I said, no, I didn't do that. But what it was, so there's this system called OpenSSL, which is what basically the way your computer talks to other computers and other servers, and it's ubiquitous. It's like all around the web. And it's actually an open system, and lots of people have checked it out and whatever, but it turns out it's got this big bug in it. And it totally like reveals your passwords and reveals, well, actually, I don't think it reveals your passwords. I think it reveals more the password hashes, which is not quite as bad as we talked about the other day. But it definitely enables you to get information from a computer system just by like going to that computer system, which is kind of crazy, right? What it is the reason they call it the heartbleed is there's when the two computers are talking to each other, there's a request you can make that says, I'm going to send you some data. Please send it back to me so that I know the connection is working properly, right? And if you use that and you send, like, I don't know, 100 bytes of data, right? Well, you're supposed to get 100 bytes back. Well, what actually happens, as far as I understand it, and I may be a little wrong on it, but as far as I understand it, what actually happens is you say, hey, give me 100 bytes back. And the computer that you're talking to actually says, OK, here's 64 kilobytes back. And it's like random stuff from your memories, from your memory system that could include passwords and other things, right? Not good, right? So it's completely like a bad thing. I was actually reading about it on Reddit yesterday. And this is what the top comment says. This may be the biggest security vulnerability of all time, right? So we're not, and that hyperbole aside, right? This is a big deal. Okay, it says this scope of this bug can't be underestimated. Essentially, an attacker can connect to any server running OpenSSL and steal anything in process memory, including the encryption keys. Including the encryption keys, actually. That is kind of bad, actually. All right. So there's actually some other interesting comments here. Let's see, and some non-interesting ones. Let's see. Here we go. Somebody says, remember, checking services for the OpenSSL heartbleed is actually illegal in some countries. So don't go and read up on how to do it and go try checking places. And then somebody says, Somebody says, what does it do? And it's the heartbeat thing. It allows a client to say, here's n bytes of data. Please echo it back to me, and then send the data. And you actually get lots and lots of other data. OK, so kind of bad news. And it goes to prove a point that this web security stuff is not 100% infallible. Even with open source software and even with thousands of people looking at this code, bugs get missed and important bugs get missed. Like 2/3 of the internet's now not secure. Which means that over the last couple of days, a whole bunch of systems administrators have been burning the midnight oil because they've been trying to fix this stuff. Questions on that? thought it was pertinent to what we discussed the other day. OK, let's talk about our next project. So this next project, I actually, hopefully you got an email about it, or Piazza. It's on Piazza and on the web page. Here's the deal. So I mentioned this the other day. What it is a song search. And you're not searching for the title or the artist. You're actually searching for words in the lyrics. In fact, one word each search in the lyrics. You're not searching for like sentences or sets of lyrics. That would be kind of another order of magnitude harder than this project already is. And this is going to take some time to actually build this, because I've really given you very little code to begin with. I've given you a read-in file that reads the data in, and we'll talk about the details of that. And I've given you a hash function in case you want to use a hash table that you build. And I think that's it. Right? I've given you part of a make file, so you have to put your files in that. Yeah? You can use C++'s you can use C++ standard library class template classes, but there isn't a hash table one, believe it or not. There's a map which, believe it or not, is not based on a hash table. It's based on I believe it's a red-black tree in general, which we haven't talked about red-black trees. But in general, it's a different type of structure than a hash table. But it's still going to be relatively fast. So you certainly could use that, yeah. And it might be faster than the hash table you create. I don't know. But anyway, we'll get into some more details about that. Here's the deal about the database. So it's 172,000 songs, right, which is a lot of songs. I don't know where this database actually originated from, but I believe it's like users typing in lyrics. So there's some garbage in it. And we'll do a couple practice searches with the program I already built to do this. And I'll show you. It's about 200 megabytes big, right? And in today's 200 megabyte file is not huge, but it's enormous for like it's enormous compared to the stuff we've already been dealing with, right? You're going to have to read in 200 megabytes and then format it into some data structure so that you can search speedily, right? So that's the deal. You've actually got 2 full weeks to do it. The first part of the assignment is due next Wednesday, which is this design document. Now what this is because this project is very open for your own structures purposely, and by the way, this has been a project before, so it's not like it's been tested that this, like, you guys can do this stuff. It's just a matter of there's a lot of thinking that's going to be involved with actually coming up with the design itself. So by next Wednesday, you'll have to come up with a plan, think the project through, and then see a TA or me or Bruce and get it signed off that we've talked to you about your project in some form or another. Okay? I mean, if it has to be over email or whatever, that's fine too. But please either see somebody or have some sort of deep email discussion about your project such that we can buy off that you're kind of going in the right direction. Okay? Once you do that, and that doesn't mean you can't start programming it now. Just know that if we don't think you're going the right direction, you may have to change some things. But you probably should start putting the files together and like getting the structure built for the programs, because it's going to be somewhat advanced. The following Wednesday is when it's actually due, and that's when the code is due, and you'll be having to do another provide for the actual code. Questions on that part? Nope. OK. Let's look at an example run of this. And remember, we are searching for words in the lyrics. Now, I happen to not give a particularly great example here. If you are looking through this database, this is the 200 megabyte long database, and you search for the word Boston, right? Well, one of the songs that's Boston is a song by Kenny Chesney. Anybody Kenny Chesney fans? Country Western fan or country fans? Country Western or country? Just country, I think. Anyway, he happens to have a song called Boston. That is not, like, the title is not what is getting searched for here. The Boston that actually gets found is in the text of the actual lyrics. So she comes from Boston, works at the jewelry store, right? Whatever that means. And thanks, Kenny. And but anyway, notice a couple things about the difference between my search term and what got picked up. What's different about those? Doesn't care about case, and the punctuation is actually also not in the search term. So what happens is we've given you a reader that you can put into your program. And what it does is it reads through the file and it picks out the title and the artist. And you will have the title and the artist, and then it gives you one word which includes just the word plus the punctuation, but not the spaces. So basically it goes, where's the space? Grab everything between spaces. That's your next word. So one of the words is B-O-S-T-O-N, comma. So in your code, you're going to have to somehow strip out that comma and make it lowercase. Relatively easy to do. In fact, I'll put a little post on Piazza on how to go about doing that part. But what it means is, first of all, you're going to have to store the song information, like for all the songs, in your database, which is going to take up a lot of space also. But you need to store it in such a way that you can search for the lowercase word, pick up the uppercase word, and then still print out the fact that it was uppercase with a comma after it. Okay, it's going to be a little tricky to do that. As far as the context goes, the title and the artist is going to be part of whatever song object you have. The context is going to be the 5 words before the word and the 5 words after the word. And if it happens to come at the beginning of a song, like let's say it's the 3rd word of a song, you're only going to print the first 2 words of the song and then the word and then the next 5 words after that. Does that make sense? Read the document. If you don't understand it, please put a question on Piazza. We're perfectly happy for answering those. Now take a look at this. So the first one, context, was she comes from Boston, works at the jewelry store. I think that's the first line of the song because there's only 3 words before Boston in that case, not 5. Now if you look at the next one, okay, so while they're talking, she's from Boston. That Boston also gets picked up. It happens to be the same song because Boston is multiple times in the song. And 1, 2, 3, 4, 5 words before, and 1, 2, 3, 4, 5 words after. There's another Boston in here, but that will get picked up in the next iteration of the search. In other words, it's going to pick up Boston however many times it finds it in the lyrics. Now, 170,000 songs. You are not going to be if you search for and, you're not going to return 170,000 songs, right? You're going to return the top 10 songs. How do you determine what the top 10 song is? The songs that have the most number of that word in them. Okay, so you have all your songs, and then whatever the top 10 are that have those numbered words. If there's ties, I don't care. Print out one of them. So let's say that the 10th one has 22, and the 11th song also has 22. Whichever one you print out, I'm happy with. Okay, so kind of up to you. It's not going to be as deterministic as it probably should be, as we talked about in the grading thing earlier. But it's going to be I don't want to overburden you with the determinism for this part of it, right? So basically, search through all the songs, give me 10 songs, and all the different places in each of those 10 songs that that word appears. Does it make sense? Okay, question.
You said so the song Boston never had Boston in the lyrics. Does that have come up or
no? If the song Boston didn't have Boston in the lyrics, it might be a dumb song, but that's a different story. But not necessarily. But yes, no, it would not come up in the search. You do not have to search through the titles and the artist as well. Yeah.
You said don't worry about punctuation. What about things like plurals and possessors?
Good question. If it's letters, you have to worry about the whole thing. So for instance, if you typed in S-H-E-S, right, that would come up because there's no space between that's a punctuation that's going to get stripped out. S-H-E-S does. If you searched for the they would not show up because you do not have to individually look through words and see if they fit. It's basically strip whatever the word is when you strip out the punctuation. That's what's going to get matched. Okay? And I mean, look, we'll be a little bit lenient if you match some things a little bit. If you don't quite get it perfectly, I'm not going to stress about that too much. Yeah, Jason. If you typed S-H-E-S, it would pick up she's because the punctuation will get stripped. Like you will be given the word S-H-E'-S. And when you strip it out, it will become S-H-E-S. And that's going to be in the read-in function. Well, no, the read-in function will give you S-H-E'-S. I will put something on Piazza that tells you how to turn that into S-H-E-S. I'll put that on there, so no worries about that. Question back. We had another question back here. Yuval, and then back here, and then, yep.
Can you search up phrases or sentences?
We're not going to have you do phrases or sentences. That's kind of another level of order of magnitude. I guess I would be perfectly happy if you said, I want to do that, and then could probably work on some extra credit if you wanted to, now that I think about it. I mean, if you wanted to. It's just going to be it's a whole other ballgame because then you have to somehow walk through lists when you find a word and see if the phrase, I mean, it's trickier. It's trickier, yeah. James?
What about plurals?
No, plurals only count if it happens to be a contraction. So if you search for come, C-O-M-E, right, and it would not pick up that comes up there. Okay? So yeah, good question. Same question. Yeah. Do not worry about plurals, and don't worry about like parts of words. Susie. You can search for a word with punctuation. Yep. Yep. So that will strip it out. Yeah. You should. Let's think about this. Yeah. Yeah. Well, here's the problem with the read in stripping all the punctuation. When you print out the lyrics, you don't want it. You want it to have punctuation. So the punctuation has to get at least as far as your program so that it gets to, so you can take it and put it in your song. Now, here's an idea for how to make your song, right? Your song class or whatever. You have a title and an artist, and then you have an array of every word in the song, right? And it should be really the words with the punctuation, because then you'll be able to print out the whole song with the punctuation correctly. When you actually store the location of that word, store it without the punctuation, but point it to the one with punctuation. If that makes any sense, process that a little later, but that's the idea. Okay? You have to get the punctuation far enough so that you can put it in your database so that you can pull it out later. Okay? All right, other questions on this one? Yeah?
So if you search for S-H-E'-S, if there was a word S-H-E-S in the song.
Yeah. If you type in S-H-E'-S and the word happens to be S-H-E-S, then it should also pick it up. Now, that's just because of the way we're defining this, but yeah, it's gonna strip the punctuation and then match just the letters. Yeah, I suppose digits too. Maybe not digits. I'll have to think about it. But anyway, I'll write the function that will allow you to do that. Yeah, Alexa.
Is there any way to avoid searching through every word of every song, or do we just have to do that quickly?
Well, it's a good question. So when we talk about these things called sets, you may not have to search through every word. You will, in some sense, have to have a list of all the words in some map, dictionary, hash table, set, something where you've got all the words so that you can match them, right? You will also have to have every word in the whole text so that you can print out the context as well. So this is going to take up a fair amount of memory, probably half a gigabyte each or something, as it turns out. Maybe not quite. Okay? All right. I'm sure you'll have more questions as we go. Yep. Allie?
So you said that if there's a song, like we're searching the word and, you only want to print up the top 10 songs?
Yes.
And then the top 10 instances of and in that song?
No, however many it happens in that song. So if you search for and it comes up 500 times in one song, print out all 500 for that song, and then 300 times in the next song, print out all 300. Okay? It's going to be, I'll show you in fact, let me just show you the example right here. So I actually wrote this oops. Oh no, what do I searched for clear. So I wrote this up in, I actually wrote this up in Python. And let me put it this way. So Python is not known for its being a speedy language to begin with, but to read in the whole file and process it takes about 3 minutes on my computer. Right? And I tried to make it as fast as I could in Python. So think on the order of 3 minutes. What it's going to do is it's going to read everything in and then wait for more queries. So you're not going to have to read the whole file, read the whole file for 3 minutes, and then do it again. So it'll act like this. Okay? All right. Somebody give me a word to search for. What is it? By the way, this list is it's lyrics of songs. So it's not cleaned up and there's dirty words and things. So just be prepared. You may see some words you don't like. Anyway, what was the word I didn't hear? All right. All right. Veggie Tales. Oh, that's funny. Okay. So I bet you didn't expect that. So yeah. So anyway. So here's what here's what it looked. So it happens to be. The first one happened to be this weird, yeah. I may have to take this off the video. But anyway, so you did this to me. Let's search for something else. Tufts. Well, let's see. Plastic tufts of polyester. That doesn't really count, right? Tufts, T-U-F-T-S. So anyway, you can do the search, and this one happened to only come up with 2 things. If it does not come out in your search, A, B, C, D, E, F, right? All right, this is a big deal. This is a lot of songs, right? A, B, C, D, E, F, G, H, I, J. All right, there we go. It should just print any report. Yeah, I told you it's got song lyrics. We are all adults here. We can deal with it. Okay. Anyway, anybody want to give me let's see if we can find one that's not like vulgar. Jumbo. Uh-oh. There we go. All right. So anyway, right? Yeah. So what'll do that? Now, notice how fast it actually did. Notice how fast it did the search. Right? Searches happen like that. Right? Why? Because the data structure I used is efficient. It uses a hash table and some other things, and it's relatively efficient. Reading it in 3 minutes. Searching very fast. It's the exact same thing Google does, by the way, right? Google reads in searches and then takes like a long time to create this database. But they leave it in memory on all their servers, and they have the ability to search through lots and lots of text really fast because of the data structures they use. They have to. Okay? Yeah. Dylan?
So there are going to be 5 words before and 5 words after.
Yeah, if 5 words are before in the thing, like this one. This actually picked up this jumbo here, right? Proper, with Lance, jumbo. Those were the 5 before that jumbo.
And then the after, though, there are only 4. Did it pick up the period as it counts?
Which one? Sorry, which one?
Jumbo shrimp since I'm prepared.
You know what? I'm gonna guess that either I wrote this wrong, right? I might have had a bug, or if I didn't have a bug, that happens to be like the last word of it doesn't sound like the last word, but remember, people type this in themselves. It's what? Yeah, it might be. Who knows? Anyway, but yeah, it should be 5 after and 5 before. Okay.
All right, cool.
All right. Any other questions on that, like the actual test? So I'm going to go. There's another slide about this, but there are going to be 2 ways to run this. One is going to be on the command line like this. Okay. And notice there's no prompt for you. Like it doesn't say what word do you want to search for. It's just boom, you just get it. And then you do have to put that little end of report thing, because we're also going to have a web interface so that you can go to the internet, pull up you can start this guy running, and then it will wait until it gets a query from the web page you go to, and then it'll do the search. Okay, so that's kind of neat too. All right. All right, so back to this one. Here we go. So as I said, the code that reads in the database, you're going to get the artist, the title, and then a word. And then you'll get, again, the next time you'll get the artist, title, and a word, et cetera. Okay. Strip out the punctuation we talked about. Context we talked about. Okay. All right. Yeah, Lydia.
It said you want to strip out punctuation when storing it, but
Yep.
like not when printing it out. So like, could you just like skip it when searching instead? Like,
Can you skip it when searching? I don't understand.
like just have your search saying like skip over punctuation when finding.
Oh, you could. Yes, you absolutely could. You could have it do that. The problem with that is going to be, how do you skip over punctuation? Like, let's say you had Boston, comma, and you had Boston, uppercase Boston, exclamation point. How do you hash those if you're going to do it? They're different strings, right? So you would have to figure out how to save it. And now, here's an idea. You could save it in some sort of structure that saves both the actual word that has no punctuation in it, and it's lowercase, and then whatever the actual word, like the other words that it also involve. It's up to you. I don't know that I'd suggest that. It might be too much work, but that is going to be a tricky part of figuring it out. This is, again, why we need the design document so that you can think of these things. You need to talk it over with some people. Okay? You will have 2 databases. You will have at least, well, right now we've given you 2 databases. One is the giant one. You do not need to copy that into your folder. Right? There you can actually make what's called a soft link, which means it seems like it's in your folder, but it's really in the class folder. So you don't have to worry about copying a 200 megabyte file into your own home folder. You will have another smaller one, which just happens to be Rick Astley songs, and that one you can search through very quickly, because it's only like, I don't know, 30 songs or 20 songs or something like that. So you can do that. You could make up versions of your own search as well. I guess I can probably make some other ones that are like not medium size, but like 1/10 of the size or something that's a little more robust that you can search through as well. That shouldn't be too hard to do. Good engine, take a minute or 2 or 3 to read and process the data. Bad engine, forever, right? So if you find yourself just like it's just stalling, it could be a loop that doesn't terminate, or it could be you just have a bad data structure. Hopefully we'll avoid those by having a good design. Okay, I think maybe there's a couple other comments. Yeah, a few more details. We talked about this, ranking the songs by the number of times a word appears in the lyrics. Song with the greatest number of matches comes first with all the match lines, then the next song, up to the 10 songs possible. We talked about web interface, and then you can use all these other classes if you want. Okay, if you want to create your own hash table, that's cool. You can also use the map, which is this from the standard library, the set, etc., vector, any of those you want to. Okay. Questions at this point? More questions on this stuff? Okay. Put questions on Piazza if you've got them. Sets. So we didn't talk about this before. I didn't make you build a set. It's actually a pretty easy data structure. Okay, what it is it's an arbitrarily ordered structure. What that means is there is an order, but the order is not necessarily what you think it is. In other words, you can put things into a set and then get them out in order, and every time you get them out, it will be the same order. But it won't necessarily be an order that you necessarily think is the right one. Okay, it is not a strictly ordered set in that sense. But what you do is you throw things into this set, and it just keeps the ones that are unique. So if you have, say, a song, right, and you keep getting this song, and you're going to put it in some set, if you throw the same song in the set number of times, it just keeps one copy of it. In fact, I think it keeps a pointer to the first one or whatever that you put in there. Okay, as long as you do that. I've got some code that you can use to create your sets. In fact, I have to update it. I will put that on Piazza as well. But here's what it looks like. I won't go over all the details here, but what this is saying is you've got a set called mySet, and you're inserting a string, right? And then you're going to insert a second string, and then you're going to go try to insert a string again. Well, the first time there's one object in there when it says just a string. Then when you put a second string in there, there's 2. And then when you put a string in again, it says, oh, I've already got that one. I'm only going to have 2 things now, a string and a second string. The third one you put in, called a string again, it's the same thing, so it just doesn't put it in again. That's what a set is. Okay, unique items. Make sense? The one thing that I don't have up here is you have to overload, I think, the less than sign so that it can do a comparison to know if it's the same thing or not if you create your own data structure, like a struct or a class. Okay? But I will put that on Piazza, the example of that. Okay? That's all sets are. Questions on, I think that's all I got for sets. Questions on sets? Yes?
Sort of
Lydia.
related to this.
Uh-huh.
Are we being graded on like space efficiency of our project?
Are you being graded on space efficiency? No, I would not say you're being graded on space efficiency. But if you use too much space, it might be slow, and it might crash. I mean, just because there's just too much space. But you're not being graded on that. You're being graded if it does the search properly, really, and within the time limit. I mean, we're going to have some time limit that we have to impose just because it could take forever. We probably won't. Well, I don't know what the time limit's going to be for reading in the file. I mean, it might be as much as 5 or 6 minutes, something like that. But more than like 10 minutes, and it's just not going to. We're just going to cancel it. So make sure you do test it on the big data set at some point. Yeah.
Are there going to be duplicate songs?
I do not believe there are duplicate songs. I don't know that for a fact, but I don't believe there are. Yeah. If there are, you'll find both. I mean, I'm not worried about that. Yeah. Yeah, Jason.
When you say give you a list of the choices, say like the word appeared in the song 10 times.
Yep.
And that's the most popular song. You just want to get 10 lines from the same song?
10 lines from the same song. Yep. In fact, that's going to be, you're always going to do that. You're going to give the whole song, all lines in that whole song, for every song that matches up to the 10.
So if you say like you have like 6 lines from a song or 5 lines from a song, you just like cut off the 5th line from the second song?
No. Remember, it's 10 songs.
10 songs.
And then however many in each song. So each time you should return between 0 and 10 songs. Okay? Yeah.
Okay. For the set, you say each member is unique, right? So let's say
Yes.
if you want to store the frequency of a word inside the set.
If you want to store frequencies, you're not going to be able to. However, you could build an object that has that only compares part of it, and then it has a counter in it if you want, that doesn't get stored. But that's, I think if you try to store two objects that are the same, it doesn't store the second one and replace the first one. It just says, I'm not going to bother storing the second one. So that probably wouldn't work now that I think about it. Yeah. So don't use a set for that. Not the right data structure for that. Yeah, Alexa.
This might be like the same question, but
Yeah.
so you can't really use the set to store the words of the song because it won't insert them more than once.
Right. You're probably not going to use the set to store the words of a well. You probably could say, hey, what words are unique in this song? That's an idea. I hadn't thought about that, but that could be an idea. So if there's 25 ands in it, right, you could find 25. You would just have and once in your set, and then you'd say, oh, and is in this one. Now I'm going to go search through the song itself and find out where those are. So that's not a terrible idea. In fact, now that I think about it, that's not a bad idea at all. If you say what are the unique words in each song, and then somehow point the word in your hash table to that song and say what are the unique words, that might work. That might work, yeah. Yep.
Is there like a limit on the number of files we can use to build a program? So like how many classes we can
Oh, no, there's no limit. You're going to be making your own make file and putting all the things that we need to make it in there. So you can use, we'll just run make on it, yeah. Yeah. So make sure it makes. But yeah, there's no other limits. I mean, I would say, if you have more than about 7 or 8 different files, you're probably overboard for this project. But, I mean, if you have more than 2, you could be overboard. But I'm just saying, I mean, like 7 or 8 would be like, you're probably overboard on it. Yeah. Yeah, Yvonne?
We decide to implement a hash function.
Uh-huh.
Will we be graded on the quality of the hash function?
Good question. I've included a sample hash function that works great for this sort of thing. So if you want to create your own hash function, I'm happy for that. But it will probably, if it's not fast or it has too many collisions, it'll be slow in general, but there is a hash function that we have given you in the code that you can use if you want, and it works fine for this. It lets you put in any length string, and it will hash it down to like a fixed length. So it's pretty good. Yeah. Other questions? All right, we'll talk more about it on Monday and as we go along. OK. Topic of the day that's new. We are going to start talking about these things called graphs. And what I mean is the thing on the left, not the thing on the right. OK, when you think about a graph, you might think, oh, I'm going to see like a chart of something, right? No. In computer science, graphs look like this. OK, they have what we call vertices and edges. OK, and we will get into all the details. And then sometimes they have arrows, and sometimes they don't. OK, that's what a computer science graph is. In computer science, graphs are actually used for a huge number of things. It's kind of, in some sense, it's a little crazy that we get to it as late as we do in data structures, because you do see them very often in other types of programming and data modeling situations. But they're also a little more advanced than some of the other things too. So that's kind of why we get to them now. But you will see these things. They model real data in many different scenarios. We'll talk about some specific examples of that. And we will see what's important to know about graphs themselves. OK? Here's what a graph is. It is a general data structure, very common. And it's similar to a tree, right? It's node-based. It's non-linear, right? And it's going to have links between different nodes. The thing is, it does not have the same structure as a tree. Right? The nice thing about trees were they had very specific structure, right? You've got parents and you've got children and you've got, you can kind of think of graphs as like the incestual part of a tree, right? I mean, it's got like circles and things, and like there's no parent and child relationship here, right? So it's definitely a little different. Okay? I told this earlier today. There's a book I read years ago by this guy. It's a science fiction kind of book about this guy who travels back in time. And I think he travels back in time twice into the same time period. In the meantime, he gets a sex change, ends up like becoming his own parents, both of them. Very odd story. So I have to look it up someday. It's very wacky story. Okay, anyway, so this is what a tree is. I mean, sorry, this is what a graph is. Tree-like, not the same structure. So we've got to deal with it in a different way. Simplest type of graph are these graphs called undirected graphs. Okay, undirected graphs are have lines that are, we call edges, that go between the circles we call vertices. Singular is a vertex. Okay, and they do not have arrows on them, meaning they are kind of bidirectional. Like there's no direction between the vertices. Okay, going between the top one and the bottom. Well, there's between the top one and the left one here. There's no directionality there. Okay, they're just connected. Okay, the graphs can be labeled with V for vertice, or vertex, and E for edge. And you generally label them. There's not necessarily any method to the madness as far as labeling goes. Okay, you just label them with the number of edges versus the number of vertices, and you can have vertices that in this case there actually are vertices that connect to two different edges, right? You can have them connected as many as you want. You could have a completely connected graph where every vertice is connected to every other vertice through an edge, but that's kind of rare. Okay. I had this example earlier, and I completely messed it up. Like the lines were completely wrong. They were not the same at all. And the other class was like, no, that one's wrong, and that one's wrong, and I'm like, oh, forget it. So I think I fixed it now. The actual pictorial structure of this is not important. In fact, not important at all. Okay, I mean, you can draw it such that you take into consideration some various features of it, but you don't have to. It doesn't matter. That is, as long as I did it right this time. The one on the left is the same graph as the one on the right. Okay? All right. So let me give you an example of where we might use graphs. Okay? There's a game that I guess it's called the coin game. I don't really know. But what it is you get 3 coins. Okay? You have a head. You have them laid out like this. A head, and then a tail, and then a head. Okay? And the object, okay, is to go from head, tail, head via a series of flips to get to tail, head, tail. Okay, and those flips are going to follow a certain set of rules. Actually, pretty easy rules. Anybody seen this game before? It's not particularly hard. It's like about on the level of tic-tac-toe, really. Not even, right? But here's how it goes. Okay, you want to go from heads, tails, heads to tails, heads, tails, and the rules are the following. You can flip you can flip the middle coin anytime you want. Okay, so you could flip it, whatever. You flip that as many times as you want. You can flip an end coin only if the other 2 coins are the same as each other. Okay, so those are the rules. Anybody want to get me from heads, tails, heads to tails, heads, tails following these rules? What do we have to do first? Flip the middle. You can't flip the end because the other 2 aren't the same. So you got to flip the middle. That's going to be H. Then what? Flip which side? The right doesn't matter. Let's flip this one. Okay, oops. We're running out of chalk here. Then what? Flip the middle again. Right? Could I flip the tail back? I could have, yeah, but I'm not going to. Okay. Then what? Flip this one, tail, and then flip the middle, and we have arrived. Right? Not too hard. Okay, but we did have some choices in there. We didn't have to necessarily do it in that order, and if we did some choices, we might go backwards. Like we might not be continually going in the right direction, although you guys are clever enough to do that, obviously. Okay. What we can do is we could actually use a graph to solve this. Now, we don't need to for this one, of course, but we could use a graph to solve this. And in fact, for much more advanced types of games, you could use graphs in this fashion to do this. What we can do is we can create what we call a state graph. Okay, anybody taking like double E classes probably heard of state diagrams and things for double E. But we can create an undirected state graph where each vertice actually represents, or each vertex actually represents a configuration of these 3. There are 8 states. Why are there 8 states here? 2 to the 3rd, right? Because each coin has 2 states, and you can do, and there's 3 of them, and they can be in any order. So there are 8 different states here. Okay, And here's what they would look like if we did the graph. Now, these whole boxes are the vertices, right? And I put edges between them saying what the next path, like a proper path is. Okay, there are 8 states, and the lines are the moves you can make. You're trying to go from the middle top one, heads, tails, heads, all the way down around to the tails, heads, tails. And you can follow it, right? And you can say, OK, I need to go this way, this way, this way. And that's exactly what you told me to do, except I guess we went to the right. Right? We went that way around. Okay? Can you always go backwards on a move? Can you always do a move and then reverse it immediately? Yeah, every time, right? There's none of the moves where the rules rule out reversing your position. Okay? That's one of the reasons it's undirected here. If it wasn't, we would have a directed graph, which is like next slide, or 2 slides from now. And that's the way it goes. And you could also see that you could do this poorly, right? You could flip the middle, and then flip one of the sides, then flip the middle again, and then flip the side, and then go ahead and accidentally flip the side again, and then end up keeping going. You can go in a complete circle and never end up at the right place. But as you can see, this models it pretty well. Okay, and again, not more than a toy example, but models it pretty well. Okay, all right. Can always go between the states. There's one of the paths, not the one we took, but that's one path. 1, 2, 3, 4, 5. Okay. If you don't have, the corollary I would say to an undirected graph is a directed graph. That means it has these arrows on there. Okay. With the arrows, it means you have to go. You can only go in the direction from the tail to the tip of the arrow. Okay. So notice to get to the left one here, you can get there from 2 different places. Right? To get to the middle one, the one kind of stuck in the middle here, you can't actually get there. There's no way to get to that one. If you start there, fine. If you're trying to get there from somewhere else, you can't do it. Not going to happen. Okay? So that's a directed graph. Graphs can actually have these things called loops, where you actually have an edge that wraps around and goes back to you. Graphs can also have multiple edges, where 2 edges are actually in the same direction from the same vertex to the same other vertex. You don't see that too often, but it could. Right? They're pretty flexible in terms of the way we can represent them, pictorially anyway. Okay? Loops, multiple edges. We won't worry too much about the loops and multiple edges. All right. So how are we going to actually represent these? Okay, here's a graph. And the graph has 7 nodes. And this is one way to represent it. Okay? We can represent it in a table that lists, on the left, it lists all the nodes, all the vertices that are starting ones. And across the top, it lists the ones they're going to. So for instance, vertex 1 goes to 2, it goes to 3, and it goes to 4. And there's 3 trues in that first row up there. Okay, pretty straightforward. Nothing too crazy about that, I don't think. Okay. What is not so good about this structure? Yeah, Brett. It wastes space, absolutely. Yeah. Why does it waste space? It wastes space because look at all the falses in there, right? As I said, you can have a completely full, a completely full graph, right? But you don't normally have that. There are some networking situations where you have that, where like if every computer is connected to every other computer directly, that might be pretty fast, but lots of wires, right? You're not going to see that too often. Some switches that connect networks do that, but not you don't see it that often. Susie? Could directed graphs have directions both ways? Absolutely. Yep. Multiple edges per set. And so if there was another one going from 2 back to 1, and over here it would just say 2 goes to 1 as well. So yeah, you could do that. Yep. In some cases we won't talk about, like we're not going to talk too much about those types, but you certainly can. Okay? All right. Other questions on this? So this is not a great way to store this. So number 1, it wastes space. Number 2, what's the space complexity of that table over there? N squared. It's actually, v squared, I guess, right? Because there's v vertices, and you need v squared amount of space for it. So that's not so good. Can anyone think of a better way to store that data? Having nodes point to each other?
Or like having a structure with a value and the value of the vertice and like an array of other stuff.
Was that what you guys were? OK, that's one way to do it. Have the value of the vertex and then a list, say a linked list or some other list of the ones it's pointing to. Yeah, that's a good one. Is that what you're going to say too? OK. Anybody else? Richard, you're going to say something else?
I think it's
Similar? OK. Somebody earlier said, what if you turned it into a tree structure or something like that? Problem with that, again, is this kind of circular nature, and there's no real parent-child relationship here, so it's a little tough to do that. But yes, but I definitely like the idea of having a list of vertices, and then just saying, or having a table of vertices, and then a list of what it's pointing, what each one is pointing to. It's going to generally save space. Okay, this is called an adjacency list instead of an adjacency matrix. Right? It's on the order of the number of edges plus the number of vertices, which is not so bad. Not v squared in that sense. Okay? Yeah, question. Would it be slower to find? Sure it would. Yeah, it would definitely be slower to find because of the fact that you've got to walk through a list or have some, it could be an array, which isn't too bad. But yeah, it would be slower, sure. But again, you're trading off space for speed in this case. Yep, good. All right. So let's see. You can actually store these with a hash table too. If you hashed the keys and then their values were the lists, right? It's kind of actually just a hash table where you hash the keys and then the list determines what the values are, or of the edges. You could do that. You don't believe me, Susie? You're looking at me like I'm crazy? Yeah. Lydia?
Okay, so you said before that like the standard map is not based on hashing, so like
right.
This is a type of map then.
Yeah. So yeah, very good question. So unfortunately, when we say hash table, sometimes we mean map, sometimes we mean dictionary. They're really synonyms to a first approximation. What happens under the covers is completely up to you, like whoever designs it. So a map takes keys and stores their values in a table, probably with the key, so that you can search for them relatively quickly. Now, depending on how it's developed, how it's done under the covers, could be a tree or could be a hash table. So it's a little one of these hazy ones. But yeah, that's what I mean when I say that. Keys versus values. Okay? All right. By the way, notice 6 has no edges going out of it, right? Because 6 you can only get 6. You can't go from 6 to anywhere. Okay? All right. We can also, and this is where it starts to get kind of interesting. We can also start to, we can represent graphs with these things called weighted paths, or the cost of the edge. Okay, and this is where it starts to get really interesting because lots of data actually falls under this model. What it means is, in order to go from vertex 1 to vertex 2, you pay a cost of 2. Like that's the length of the path. Now, the cost can be any metric that you want. It could be distance if you're talking about going between cities. It could be the cost if you're talking about how much does it cost. This isn't true necessarily anymore, but it used to be true that calling different cities cost more money, right? So you could, I guess if this was like the world or something, calling, let's say V1 was the US and V2 was Vietnam or something, it might be really expensive versus V4 is England and is not as expensive, or Canada or something, right? So there's lots of choices here where you end up having these associated costs. Okay? And what you generally want to do is find the cost from one vertex all the way to another vertex. And what you do, it's easy. You just add up the costs as you go along. The key, though, and maybe you guys, I think I saw, were you going to ask something, Ed? No? The key here is that some paths actually cost less than others. And it's probably important, in fact, it's very important, to maybe find a way to figure out the least cost path. Okay? So we're going to talk for a little bit about that. The point is, you can weight these. You can then, if you want to go from one vertex to the other, you just add up the cost to get there. Yeah?
So is this how like Google figures out the shortest path to get to some place or like the cheapest?
Yeah, yeah, that's a very good question. So Google Maps, right? Google Maps uses these sorts of ideas probably in a much more robust fashion, but yeah, it definitely does that, right? For instance, it might be to drive from here to San Diego, California, right? Here to San Diego, California. You could go a lot of different ways, right? Google's going to hope to try to tell you probably the best way. Now you can do it based on distance. You can do it based on time. You could do it based on, I don't know, scenery or something if you want. But you can base those costs on various things. So it might be faster to go all the way across on Route 90 and then down somewhere in like Idaho or something, right? But the shortest path might be to kind of weave your way through kind of the middle states. But it's going to be, in the end, it's going to take a lot longer because you're on some back roads and things, right? So cost is all about like what your metric is in this case, okay? Lots of different examples of that. Let's see another example. So let's say, let's go back to the telephones for a second. If you call from here to California, actually, funny story. When I taught physics, I used to talk to I taught like 9th graders. And one day, one of them was asking me about battery life or something on their cell phone. And I said, yeah, did you know it costs, or your battery dies faster the farther away the person is that you're calling? And so they're like, no, I didn't know that. And I totally convinced them that if you call like Australia, your battery will last for like 2 minutes on your phone, right? I also convinced a kid that they make hot dogs out of sawdust, but that used to be the case. No, it wasn't sawdust. It was recycled paper. That's what it was. He said, what happens to all this recycled paper? And I said, they make it into hot dogs. And he goes, they do not. And I said, they do. And then he believed it for like 3 days until one of his friends called him a dumbass, and then he was in. But anyway, whatever. So anyway, back to the phone call for a second. So if you're calling from here to California, okay, does anyone know what path your signal actually takes? So it goes from your phone, if you're have a cell phone, it goes from your phone to the local tower, which is somewhere within the Boston area. And then it goes where? Any ideas?
The satellite.
Sometimes it's a satellite, okay? Sometimes it actually is a satellite. Sometimes it's through a ground, like through the actual like underground cables, or above ground cables, I suppose, across the whole country, right? If you do the satellite route, okay? First of all, does anyone know how far away certain satellites are, like the International Space Station? About how far away they are from us?
Further than others.
Further than others, thanks. What was that? Yeah, between 100 and 200 miles really is about where the International Space Station is, right? It's not too far up. I mean, 100 and 200 miles. It's small, and you can't see it. But anyone know how far away the? Well, here's the problem with making a communication satellite out of a satellite that's only 200 miles away. You've all seen movies where they have like it's Apollo 13 or something. It's going around the Earth, and every 3 hours there's like a sunset, right? You've all seen that. Well, the reason there's a sunset every 3 hours is because it's going at 17,000 miles an hour, and it doesn't have to go that, like it's only 17,000 times 3 miles around, and so it continually goes out of like sight distance, right? Ah, there you go. So there's other satellites which are geostationary, meaning that they set them up at a place where they take a whole day to go around the Earth, and they set them up at the equator, basically. And so in 24 hours, they take 24 hours to go around, so they stay above the same location. How far away are those satellites? Pretty high up? Ideas? What do you think? They'd actually have to go slower because it's 24 hours instead of 3 hours to go around. So they have to go a lot slower. Well, actually, they have to go a lot farther. They do have to go a lot farther, that's true. But it turns out it's farther away. But ideas how far? Anybody want to guess?
50,000 kilometers.
50,000 kilometers. You're actually very close. It's something like 30 to 40,000 kilometers away. Yeah, which is a long way, which means they're far enough away. This is where this is all going to. They're far enough away that it takes about a quarter of a second for the light to go, for the radio wave to get from the cell phone tower here, or wherever the ground station is, up to the satellite, and then back down to the ground station in California. 0.25 seconds, which you can hear as a delay when you're talking to someone, right? I don't know if you've ever tried to like talk to someone and like coordinate your speech or sing with someone. Forget it. It's not going to happen on the phone. Too much delay. But you can tell if you're on a satellite link, if the delay is more than what you normally expect. Okay, because going across the ground while not at light speed is a much shorter distance, 3,000 miles instead of 40,000 miles up and back, right? So it's kind of, you can tell that. But anyway, the point is, in a graph of this, the distance to the satellite might be the cost, right, to get the radio waves from you through the whole system to the other side. The distance might be. Does anyone know how long it takes our messages to get to the Mars rover?
4 hours?
Not 4 hours. Good guess. Not 4 days. You're going the wrong way.
4 minutes.
4 minutes. You're close. It's about 8 minutes actually, which means. No, that was good. No, that's not bad. It's 8 minutes, right? But what that means is, so some engineer at NASA is like telling the rover to go somewhere and go left and go find that rock. It takes 8 minutes for the signal to get there, 8 minutes for the signal to get back. So 16 minutes later, the guy gets the thing from the rover saying, I don't want to go left, or whatever, right? And then 8 minutes, 16 minutes later, it does that, right? So light speed is, remember, finite. Okay, back to graphs. So this is another example of the type of graph we might use that has costs associated with it. The graphs that find the shortest path for airlines, not necessarily the shortest path, but the shortest path given the different hops you have to take to get from point A to point B, right? If you want to fly from here to like Oklahoma, right, you can't go necessarily directly. You have to go here to Dallas and then Dallas to Oklahoma. And that whole pathfinding algorithm is all about graphs. Okay? It's all about graphs in this case. Okay? All right. Well, what is the shortest path from vertex 1 to vertex 6? In this case, how do you get from 1 to 6? You can go 1 to 4 to 6, and that takes 9, right? Or you can go from 1 to 2 to 5 to 7 to 6, and that takes 12, 18, 19. Or you could go 1 to 4 to 7 to 6, which takes 3, 7, 8, right? So 8 happens to be the minimum, unless I did my math wrong on this one. Right? 1 to 4 to 7 to 6. 1 to 4 to 7. Oh, no, right. No, sorry, I did count wrong. So 6, yeah. So it's going to be 6. And that's the weighted path. The shortest unweighted path, right, goes 1 to 4 to 6, which if you didn't count the weights, it would only be 2 hops, right? Make sense? So you've got a difference between the weighted path and the unweighted path. Okay, and sometimes it's less cost to go down the longer, in terms of number of vertices, path than the unweighted one. Notice no path from 6 to 1, can't get there. Okay, so not my phone, is it? I used to have a rule in my the classes I taught in high school that anytime a phone rang, I got to answer it, and if their phone rang, or if my phone rang, they got to answer it. That happened once or twice. One of my friends like, who's this? It's funny. One of my kids answered, this is Mr. Gregg's class. It's funny. Anyway, okay, so some graphs actually have negative weights. Okay, you can have a negative weight. Look, the negative 10 between 2 and 5. That actually screws up this whole pathfinding least cost thing. Let me show you why. If you want to go from 5 to 4, what's the cost? 1, because you go directly 5 to 4. What if you went 5 to 4 to 3 to 2 to 5 to 4? You're still going from 5 to 4. You're just going a nice circuitous path. 5 to 4 is 1. 4 to 2 is going to be a total of 4. Then 2 to 5 is a total of negative 6. Negative 6, and then 5 to 4 gives you so negative 5. So if you go around twice, the least cost is actually negative 5. Well, why stop there? You keep going, right? And you keep going, getting lower and lower and lower. So this is an undefined shortest path in this case because it has what we call a negative cost cycle. And it's not necessarily a very good thing. Like there are cases where you would have negative paths. Some electrical engineering situations where you put batteries in and they have negative costs because the battery's like adding energy to the system and so forth. But in this case, you're not going to be able to find a shortest path because it just doesn't exist. Okay, so we probably won't talk about those negative ones too much. Okay. All right. So what we're going to do is we're going to try to figure out how to do this shortest path via an algorithm, because that's actually kind of important. That's exactly what Google does when they do their Google Maps, right? They have to have some algorithm that figures this out, right? And they're pretty smart, but we can figure out some path-finding algorithms too. OK? So here's what we're going to do. All right, well, does anybody want to give me an idea of what we're going to do? Like how we might go about this? How might we go about finding the shortest path via an algorithm? Yeah. OK. Yeah, go ahead, Vivek.
Could you like try all the paths and then return the shortest one?
Yeah, you could totally try all the paths, right? In fact, the first thing we're going to really try is kind of like that, which is not really the best way, because that's going to be an order n like v squared sort of way. But we will. That is definitely one way to do it, right? Just go down all the paths and figure it out. So that's definitely a good way to do it. In fact, what you would do in that case is what we call a breadth first search, which is exactly like the breadth first searches we were doing for breadth first types of level order searches through a tree. Okay, it's the same idea. So let's go through and do this. We pick one to start. So what we're trying to do is we have one to start. In this case, I'm going to pick vertex 3. And we're going to call that the start. And we're going to say we're going to go from vertex 3 to all the other vertices and see what the shortest one to each one is. Okay? Immediately, you can say that it doesn't take any cost to go from 3 to 3. Done. Then look at all the vertices that 3 points to and go to those ones and just add 1, because this is an unweighted shortest path, right? So you're just going to add 1. So 1 and 6 both have 1. Okay? And at this point, by the way, we are done with 3. There is no other way to get to 3 and make it a smaller cost. Same with 6 and 1. They're both going to be done as well. You can't go any less than 1 if you've started at 0 and have taken 1 jump to get there. Okay? All right. Then you go and you pick either 1 or 6. It doesn't actually matter in this case. If you do 1, then you go from to the distance of 2. Okay? And in this case, it's vertices 2 and 4. And that's going to be from 1. And there aren't any paths to any other from the 6 to any of the vertices. So if you go to 6, there's no other ones to check. Okay, so 1 and 6 are done. And now we're at 2 and 4. Let's go with 2. Okay, if you go with 2, what you do is you actually disregard. First of all, you disregard any that have actually been calculated already, right? That have been gone through already. So we haven't actually gone through 4 yet. We've marked it to begin with, but we haven't like set it aside as being done with. We haven't figured out what its vertices are. So 2 goes to 5, and that's going to add 1 more, so that's going to be 3. You could go back to 4, but that's already 2, so that's 2 is less than 3, so you're not going to mark that as 3. You're not going to go again bigger than that. Okay? And then let's see, we can get 7 from 4. And we go to 4, and 4 adds another one, and that's also going to be 3. And at that point, we are done. Okay, see how that works? It's a breadth first search. Not really the best method because it does look through all of them. But the good news is that we can do a little bit better. Okay? All right. Here's how we're going to actually turn that into an algorithm, okay, into code. We can keep a table that looks like this. The table will say, here's all my vertices. I'm going to mark them as found or not. Well, I'm going to mark them as known or unknown. In other words, false if they are known, if they are not known yet. True if they are known. And then I'm going to list the distances. And I'm going to start with labeling everything but the start in infinity distance. Because that just means that, well, we don't know what it is yet. Okay? If you're doing this in code, infinity can be the biggest number that you can plug into your computer and mark that. Or it can be some other sentinel that you have. Yeah, Al?
Why is V3 false?
And well, we haven't actually processed it yet. That's the idea. Okay, we're starting out and we're saying, okay, that's where we're starting. So we know the distance is 0, but we haven't actually looked at it and its vertices yet, or its edges yet. Okay, all right. As you go along here, okay, you change the table by looking at a vertex, seeing its edges. Okay, once you look at the edges, you mark that node as being known, and you add 1 to the edge. And that's all you do. Add 1 to each edge. Okay. Here's what it looks like in code. Don't stress about this code. This is actually not so great because it's a v-squared algorithm. Okay? And by the way, if you had a graph that looked like a linked list or something like that, right? Then it would actually be v squared because you look at the first one, then you look at the second one, and then you have to look back at the first one again, and et cetera. You have to look at all the other ones to see if you're actually connected. Not such a good algorithm. Yeah, PB. You can do it with recursion. This one happens to not be. You can do it with recursion. You can also do it with, well, you can also do it a slightly different way, the way we did the breadth first search with trees, which we'll get to in a couple minutes. But let's just quickly go through how this table actually comes out. Okay? Start at 0 again. Start at vertex 3. You look at vertex 1 and 6. Okay? You mark 3 as known, and then you mark 6 and 1 with a distance of 1. Okay? Then you go to either 1 or 6. Okay? You go to 1 or 6 and you mark, let's go to 1. We mark it as known after we add 1 to its vertices. So 4 and 2 get 2, and then 1 is now known. And you don't need to actually go back and look at the 0 in this case, okay, because it's already, well, you can't get there anyway. Then you go to 6, and 6 has nothing that we're going for, so we just mark it as true, as known. Then we process 2 or 4, it doesn't actually matter. We process 2, and 2 goes to 5 and 4. The only one we need to update is 5 because 4 is actually already lower than 3, so we don't change it. And then we go to 4, and then 4 goes to 7 and 5. 5 doesn't need to be changed because it is going to be 3 from the previous one. 7 does because it didn't have one yet. It goes from infinity to 3. And then we process 5 and 3 and we're done. I'm sorry, 5 and 7 and we are done. Okay, yeah? Let's look at 4. This one? OK, so if you look at 4, we set 4 to known because we're going to deal with its vertices. Which vertices does it have? It's got 6, 7, and 5, and 3 actually, right? The only one that's going to be one more than 2 is going to be 7, because 5 was already set to 3, because 2 sets 5 to 3. 7 hasn't been set yet, so 4 is going to set that. 4 looks at 6 and says, oh, it's already less than 3. I'm not going to set it more than what it is already. And the same thing with 0. OK? Question? Doesn't matter which one. You will come up with a minimum for each one. It doesn't matter. As long as as long as you do it in the order from the node that you came from last. That's it. Yep. Susie and then Hallie. What kind of structure is the graph itself? That's kind of a tautology. It's a graph. I mean, it can be held in memory as that table if you want. Well, no, it can't. It would be an adjacency list generally, or an adjacency matrix. But an adjacency list is the way it is in general. Probably the fastest way is that. Yeah. Al?
Do you even have to look at the numbers, or do you know, like if it's already been looked at, can you assume that that value is less than the value that you're going to assign it? You
can, and that's what we're gonna kind of go into another structure or another way of looking at it that will do that. You don't need to go back and look at. So if you're at 4. You don't need to, 3 is already going to be marked as known. You don't need to go back and look at a known one because it's already got to be the minimum because of the way we did the algorithm. Yeah. Okay. The way we did it in the code, it does go. I think it does go back and look at that. So not so good. James, and then.
In a linked list, you know how many like next or previous pointers you need in the node.
Yep.
But in this case, couldn't technically any node go anywhere? And so how would you plan ahead for like how many pointers you need?
Oh yeah. Well, you would probably want to do it in an adjacency matrix or adjacency list where it has a linked list. So you can, when you populate this with the graph, you're going to know that, and that's really how it is, right? And you're going to, when you go to vertex 4, you're going to know that you're going to walk the the links and know that it goes to 5 and 6 and 3 and 7. You're going to find that out. Yeah. Jason?
So if you're setting a d to infinity when they're not known,
Yes. You do need the known so that you know not to check again. That is what we kind of just talked about. You want to not check again if you can help it, right? And we'll see how that actually works here. So remember when we did the search or the printing out of the trees, and we did that level order. I don't know if you remember, but we used a queue to do that, right? This algorithm can actually also be the same exact thing where you have a queue. You basically push in vertex 3 or in queue vertex 3 and then dequeue it and look at its edges and then set it to 0 and then set the edges to 1 more. Well, I guess it's already set to 0. Set the edges to 1 more. And then in queue both vertices and then go through the process again. Okay, it's exactly, if you want the, well, here's the code that it looks like in pseudocode, right? Basically, for each, you set them all up and you set the first distance to 0 and you enqueue that one. And then you check if the queue's empty. If it's not empty, you go and you dequeue and then you push two other, or you enqueue two of the vertices all the vertices that they have. And then when you do this in a first in, first out situation, you actually don't have to ever go back and look at the ones you've already dealt with. So this one's on the order of, let's see, the number of vertices plus the number of edges. So it's actually a faster algorithm altogether. Okay? By the way, sometimes the queue might be empty and before you've actually looked at some of the vertices. That's because you can't reach those vertices. Like there are graphs, obviously, if you were trying to, if you started at 6, you'd be done really quickly, right? Everybody would be infinity except 6, which would be 0, if you were trying to find the least path, because you can't get to anywhere from 6. Okay? All right. So that's that. On Monday, we're going to start with this next thing called Dijkstra's algorithm. It's one of the most famous algorithms in computer science by this guy named Dijkstra. He happens to have an IJK in his name, which is kind of cool if you ask me. 3 letters you don't normally find next to each other except in the alphabet. Right? And he is actually doing the same process except now with weighted paths. Okay? And this is where it becomes like important for real life stuff. Okay? Questions? All right. I'll see you guys Monday.